Hey everyone, so this is going to be problem set 9. Once again, you should work on these questions by yourself and then watch the video to check your answers. All right, now before I start, I do want to mention that some of these questions you'll notice have 4 choices, and I normally say that those are regions questions. And while that is technically true, these are actually very old regions questions. So these aren't technically part of the regions anymore, but not like it really matters for you guys. So moving on. So here they give us an object moving in a vertical circle. What you're going to end up doing is, like always, drawing an FBD. At the very bottom of the circle, we have 2 forces. We have the tension force going up of 95, and there's a gravitational force going down of 50 newtons. So the net force is going to be 45 newtons going upwards. They want us to figure out what the velocity is, so we're going to set this net force equal to mv squared over r. So we have 45 equals 5 v squared over 1. So plugging in our numbers, doing some calculations, we end up getting that the answer is going to be B, 3 meters per second. Here, they want us to figure out when will the object become slack at the top of the circular path. Basically, the idea here is that when it goes to the top of the circle, instead of there being 2 forces acting on it, there is only one, the gravitational force. Remember, during these vertical circles, the tension force is going to vary. It's going to vary depending on the speed. The gravitational force is always acting on the object and is always going down. So at the very top of the circle, there is a limit to how fast it can go based off of this gravitational force being the only thing keeping it in the circle. So if we keep that in mind, then we end up saying that we can set the weight of the object equal to mv squared over r. The masses don't matter. So we end up doing 10 times the radius, which we said was 1 meter, setting this equal to v squared. Now, when you solve for v, what you'll get is that the speed is roughly about 3 and change, right? About 3.2. Now, you'll notice that none of those answers are on here. So what they're saying is, what is the maximum speed that would keep this with a slack rope, I guess? So any speed faster than this would give you tension into the string in order to keep it in the circle. So we need essentially to round down to the closest number. The answer would be 2. So even though the object probably wouldn't actually go through the full circle, it would most likely do something like this, and then start kind of falling out of it. The rope would technically be slack. There would be no tension in the string. So that was kind of the idea for this, but this was a really tricky question for that. All right, now for question 3, they want us to figure out how many days are going from point planet A to planet X, or from start point to X. This uses Kepler's laws. So if you remember in Kepler's laws, equal areas sweep equal times. So here we know that area 1 is 100 days long. We know area 4 is 100 days long. So this is 100. This is 100. And because 1 plus 2 equals 3 plus 4, then we know that 2 and 3 have to be equal to each other. So whatever the area of 2 is the same as area of 3. Now we know that the sum of all these numbers should be 600 days. So 100 plus x plus another 100 equals 600. Gets us that each one of these is going to be 200 days. With that all being said, going from area 1 to area 2 would take a total of 300 days. You could have also realized that by realizing that, well, if area 1 plus 2 is equal to 3 plus 4, then that means that these, again, have to be equal times. So if the total time is 600, half that would be 300 and 300. Question 4. So we have an object that is following down this circle, and they want to know what dotted line represents the path it follows. Once it leaves this ramp, it's going to become a projectile, a horizontal projectile, so it's going to follow path C. Easy enough. Question 5. Here they want us to figure out what the speed is at the bottom of the ramp. bottom of the swing, sorry. Same thing as we did for question 1. There's 2 forces acting on it. There's the tension force going up of 12 newtons. There's the gravitational force going down of 10 newtons. So when we do F net equals mv squared over r, the net force is going to be 2. The mass is 1. V squared over the radius, which is 0.72. Plugging all of this in gets us C. All right. Question 6, what is the magnitude of the centripetal acceleration? So realistically, this probably should have been before 5, since it pretty much works off the same stuff. Here, instead of doing F net equals mv squared r, we're just going to do F net equals mac. Again, when it gets to the bottom of the swing, the net force is still going to be 2 for the same reasons as before. The mass, because they said that the weight was 10 newtons, that means the mass must be 1 kilogram. So the centripetal acceleration must be 2 meters per second squared. Question 7 is actually the same question from problem set 9. Once again, it's moving at a constant rate, so the speed doesn't change, which means that the acceleration should be constant and should be directed strictly towards the center of the circle, so directly to the left. Question 8. Okay, so this one's a little bit, well, at first it seems like it's going to be a tricky question, but they're saying is that how is it possible that the satellite doesn't change its speed even though there is a net force acting on it? The idea here is to keep in mind what is the main factor. How do you get it so that you are experiencing a force without changing your speed? And as I mentioned in class, that only occurs when your velocity and the force are perpendicular to each other. So the answer would be this one. Centripetal force is perpendicular to the velocity of the satellite. All these other ones don't make any sense. Again, there can't be a zero acceleration because net force and acceleration go hand in hand. Whatever happens with the net force also happens with the acceleration. I never use this term dynamic equilibrium, but what dynamic equilibrium means is that you are in equilibrium while moving. So basically, it means that you're moving at a constant velocity, which is not the case. It's constant speed, but it's constantly changing direction. So it is not in dynamic equilibrium. C doesn't make any sense because if centripetal force was in the direction of the velocity, we'd have an object that's speeding up. So that wouldn't make sense. And D, again, is just garbage. Centripetal force is equivalent to the reaction force caused by a satellite. Who cares? So the answer was E. 9. So here they want us to figure out which one of these cases would be the same if we go to a planet with same size or different mass. The idea here is the two planets are going to have different accelerations, right? The gravitational force is going to be different on these two planets. So which one of these scenarios would remain the same? Essentially, anything where we are not worrying about what's happening vertically. So if we're doing something that is independent of the vertical motion, then the forces of gravity should not play a factor in this. So uh, the rate at which each object would fall, yeah, that's definitely off the case. Those would be different. They would not result in the same motion because they're both experiencing different forces of gravity, and therefore they experience different accelerations, so they'll fall differently. The amount of force needed to give an object a horizontal acceleration. Horizontal acceleration is independent of the vertical gravitational force, so this one is correct. And then number 3, or statement 3, the amount that each one would stretch a spring. We haven't really talked about springs, but the key thing here was when held vertically. If you hold an object spring vertically and you drop it, gravity's pulling that weight down, causing the spring to stretch. That's all you need to know. So even without us talking about springs, you should recognize that gravity is what's pulling that spring down. So different gravities mean different pull downs here. So 3 is off the case. So the answer is just 2 only. Where is it? There it is. A. All right. Number 10, they give us 4 satellites and they want to know which one's closest to the Earth. This one you're kind of using part of Kepler's laws, which is essentially you don't need to know it specifically, but the fact that the period is proportional to the distance. Now, of course, that's not actually correct. I don't remember it off the top of my head. I always forget it. I have to constantly rederive it. I think there's like a t squared is proportional r cubed, but I could have these exponents mixed. But it doesn't matter because it goes back to the same idea that objects that are closer will end up having lower period. So lower period close to the object. So this one's got the lowest period, therefore it is going to be the closest. Question 11. We have an object moving in a circle, experiencing a force, and they want to know what the velocity is. It's a horizontal circle, so I don't have to worry about any sort of, weirdness with the whole vertical stuff. So this is just a straight plug and chug. We have a force of 50, mass of 10. We're looking for the velocity that's squared, and experience a radius of 5. Plug all these numbers in, and we should end up getting that the speed is 5. 12. So we have an object moving in a circle. Again, it's kind of based off of Kepler's laws. The idea that, C and D are just complete nonsense. As far as the other ones, the whole idea is that the sun is located at the focal point of the ellipse. So answer would be A. It's not actually directly in the center. It's at the focal point. This is kind of what I said before. Another part of Kepler's laws. The first one that the pathways are elliptical with the sun at a focal point. Question 14. We have a person with a mass of 75 going onto a planet that has twice the radius and half the Earth, half the mass. What is the new weight? So we're using the 1-1 method with g m1 m2 over r squared. G stays the same. The mass of the planet, they said, is half the mass of Earth. This mass doesn't change, and then the radius is going to be twice the radius squared. So this ends up being 1 over 8 times 750. So it's 1/8 of the original weight, which is 750. So if we plug all these numbers in into the calculator, we end up getting 94-ish. Oh, look at this. This looks like the exact same question. So clearly the answer is going to be 94, right? Wrong. Pay attention to the question. What is their mass on this planet? Well, mass never changes, so the mass is still 75 kilograms. Always pay attention to this. This is definitely a really nasty trick that they like to play. So sometimes they'll set up the problem so it looks like you're going to have to do a 1-1 method because, as we know, anytime you go to a new planet, your weight's going to change. But then they throw in that little last curveball of it being mass. So always pay attention to those types of questions. Pay attention to the units and all that. Number 16, we want to know what the gravity is, the acceleration of gravity is on this planet. So we're using this alternate form of the equation, gm over r squared. So the planet has 320 times 320 times that of Earth. The radius is going to be 11. This is 11 squared. So if we plug this all in, what we'll end up getting is an answer of 2.6. Now this is 2.6 times the acceleration of gravity, 2.6 times. So we end up getting 26 as our final acceleration. 17. So 17, we have an object going in a circle. We have two objects. It's standing on the surface of these two planets. They want to know what is the ratio of the weights at location A and location B. They both have the same mass, but they're at different locations. So the equation is going to be g m1 m2 over r squared. For object A, basically everything's 1 over 1, which is 1, right? For object B, everything up top stays the same, but at the bottom it's 4 squared. This gets us 1 over 16. So for the ratio, it's going to be A to B. So the force on A was 1. The force on B is 1/16. So moving things around, we end up getting it's a 16-to-1 ratio. That A is 16 times more that of B. All right, 18. Which location is the magnitude of the satellite's greatest velocity of the greatest? So we kind of talked about this as kind of part of Kepler's second law, or a combination of second and third law that as the object gets close to the planet that it's orbiting or whatever it's orbiting, it always goes faster. So it's fastest when it's closest, slower when it's going away, and that's how we get those whole equal areas, equal times. So the answer would be C. All right. 19, we have two satellites in orbit at different locations and different speeds, and they want us to figure out what is the distance of satellite B based off of what's being given. So this one requires a little bit of legwork. So what we're going to end up doing is first we're going to solve this algebraically for one of the satellites. Uh, when you're in an orbit, the key thing to keep in mind was that Fg equals the centripetal force. So G m over r squared equals m v squared over r. Keep in mind, I'm instead of using m1 and m2, I'm doing capital M and lowercase m, mostly to differentiate the planet and the object that's orbiting, or the satellite in this case. The reason I'm doing that is so that I know which mass is being canceled out. The mass that's staying here is specifically the mass of Earth. This is going to play a part as we get later on. Also, I could get rid of one of these r's down here. So if I move things around, I end up getting gm, which is a constant, right? G is constant. The mass of the Earth is constant, is equal to r times v squared. Because this is a constant term, this is going to be true for every satellite that is orbiting Earth. So for satellite 1, and it's true for satellite 2. So solving this equation, we end up getting that r1 v1 squared equals r2. Divide the v2 squared over here, and we end up getting this one, r1 and then v2 over v1, all underneath a exponent. All right, question 20. At which 2 points does the planet have the same velocity? So same velocity would have to be at same like distances away from the star. That only occurs at B and E. So at this location right here. 5 here, they want to figure out which satellite has the longest period. Again, kind of going back to what I mentioned here, the only factors that affect the speed, which kind of goes with Kepler's second law, is distance. So masses does not factor in at all. It's which one is essentially the furthest away. So the furthest is this one. All right, 22. Person's weighs 600 and goes to a planet that's 4 times the mass and twice the radius. They want to know what the weight is. If we use the gravitational force equation, G m1 m2 over r squared. The planet is 4 times that. The person's mass does not change because it never changes, and the radius is twice that here. Doing all this, we end up getting that the answer is 1, meaning that there's no change in the gravitational force. So if it was 600 before, it's 600 now. 23. All right, so this one kind of goes back to just a normal circle. What I'm going to do is I'm going to solve this algebraically, just because I like doing that. So here we have, they want to know the maximum speed the object can travel in a circle. The idea here is that the frictional force is equal to this mv squared over r. The frictional force is going to be equal to mu Fn, which is mv squared over r. Fn, because of the object being moving in a circle, we have gravitational force going down. Well, I should say it's moving in a horizontal circle. This is what my FBD looks like. So the normal force is going to be equal to the gravitational force. So this is mu mg equals mv squared over r. What I like about this is that it shows that the mass doesn't matter. So if I want the maximum speed, I'm essentially going to solve this equation. Mu gr, so it's the square root of mu gr, which in this case would be square root of 0.25 times 10 times the radius, which is going to be another 10. Plugging all that in, we end up getting 5. Okay. 24. We have a planet that has a mass 10 times that of the Earth and 5 times the radius of the Earth, and they want to know the value of G on this planet. So just gravitational force equation. Uh, Actually, no, not that one. G. G m over r squared. G doesn't change. The mass of the planet is 10 times that of the Earth. The radius is 5 times that of the Earth, but being squared. So this ends up being 10 over 25. Uh, but this is going to be, I mean, I don't have a calculator right now, but this is going to be, it's going to be this times the original acceleration of the Earth, which is another 10. So this is going to be 100 divided by 25 or 4. You always have to make sure that you um, multiply it by the original if they want it as an actual number. And then last question, 25. We have two objects. Each has a mass m and r, and the mass of each object is tripled. What happens to gravitational force? Despite this being an old AP question, this is actually really straightforward. So because the mass is being tripled, but nothing else changes, 3 times 3 over 1 squared is 9. So it's 9 times the original force, which is C. And that's it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.